If we wait long enough, a sensor like this TMP36 will come into equilibrium with its surroundings. In this case, we've got it up against the wall of a coffee cup with coffee, hot coffee on one side at temperature T coffee, and air on the other side at temperature T air or T ambient. Now we're going to pretend that both of these are really big things compared to the sensor, which is not a terribly bad approximation. So that this will act like a thermal energy reservoir, and this over here, the air, will also act like a thermal energy reservoir, as you did in thermodynamics. So what we need to do in order to find out what the equilibrium temperature for this component is going to be is do an energy balance on a control mass over here. So this control mass is in equilibrium. That means if we've got heat flowing in from this side and heat flowing out to the air side, they need to balance, otherwise the temperature would be changing. So it's a simple matter of Q in equal to Q out, and the heat coming in depends on how much of this temperature sensor is in contact with the wall and eventually with the coffee, and how effective the wall and the gap in between are at transmitting energy into the temperature sensor. So we're going to soak up all of the things that we don't know about heat transfer in that heat transfer coefficient H. We're going to multiply it by the area, this area here that's in contact with the wall, and we're going to multiply it by the temperature difference, because the bigger the difference between the coffee temperature and the sensor temperature, the more energy we're going to transfer into the sensor. So let's just make it clear that all of that is about the interface between the coffee and the sensor. The output, the H is going to be different because we've got air in contact with this surface out here, which is different from the wall of the coffee cup. But we'll still soak up all our lack of knowledge in this heat transfer coefficient that'll depend on those circumstances. Area, this time the area in contact with the air. Delta T, this time the difference in temperature between the sensor temperature and the air temperature. And we'll make sure that we recognize that that's the interface between the sensor and the air by subscripting this SA. So if we pull that out, HACS, that's all about how good this interface is at transferring energy from the coffee to the sensor. And HASA, that's all about how good the interface here is at transferring energy from the sensor to the ambient environment. The delta T, well, for the CS it's going to be T coffee minus T sensor. So there'll be a positive heat transfer to the sensor if the coffee's hotter than the sensor. And on the other side, the delta T will be T sensor minus T air. So if the sensor's hotter than the air, there's going to be energy transferred from the sensor to the air. Now we know from a practical standpoint, from observations, that the temperature here of this sensor is going to be somewhere between the coffee temperature and the air temperature. And it turns out that it's going to be a weighted average depending on which side is better at transferring heat. So if the coffee and the wall are better at transferring heat into the sensor than the air is at transferring heat out of the sensor, then we'll be closer to the coffee temperature. And if we do the math, we can come up with an expression for T sensor equal to HACS times TC, the coffee temperature, plus HASA times the air temperature, T sub A, the air temperature. So this is weighted with the HA for the coffee to the sensor side. This is weighted with the HA for the sensor to the air side. So if this is bigger, we'll be closer to the coffee temperature than the air temperature. And then, to make it actually come out in temperature units, we wind up with HACS plus HASA. So this tells us that the sensor temperature in here is going to be a weighted average dependent on how good this interface is at transferring energy compared to how good that interface is at transferring energy. Now when you're making a mounting, if you want the temperature sensor to be really close to the temperature of the coffee, then let's put some insulation on that sensor to reduce the HA for the sensor to the air side, and thus reduce the heat transfer on this side. And for example, if I wanted this TMP36 sensor to be closer to the temperature of the coffee in my cup, I could mount it onto the cup with this foam back tape that would act as a little bit of insulation to keep the air from interacting with it as effectively as the cup interacts with it. So I could put that on there like that, and that would probably give me a closer match between the temperature of my sensor and the temperature of the cup. And there's a technique you might try in the lab.